In 8.5, we're going to continue analyzing functions of two variables with derivatives, specifically looking at critical points and then trying to optimize those functions. So to understand this process for functions of two variables, we're going to go back to Calc 1 topic and look at how to optimize functions of one variable. So let's review some terminology first. The critical points of a function, f of x, are going to be the points where f prime of x is equal to 0, or where the derivative doesn't exist. And note that although this is an important detail, the derivative not existing, we're not going to focus on that part as much in this course. We're going to focus more on when the derivative equals 0, and sometimes we may even say critical points where the derivative is equal 0 and nothing more, but that is a caveat that we do need in general. The local min and local max of a function are going to be the smallest and largest function values when you look at just near that point. So for instance, a local max might be the top of a mountain in Rhode Island or in the Appalachian Mountains or something, but it doesn't mean that it's the largest point on Earth. That would be Mount Everest. That would be the global max. That if you look at everywhere, there's a biggest point. So local min and local max are smallest and largest when you look just near that point. Global min and global max are the smallest and the biggest point with no exceptions. We'll look at some more differences between local and global min and maxes in some examples. So the big thing we learned in Calc 1 is that any extrema of the function have to occur at these special points we call critical points. So if you want to find the mins and maxes of a function, you can find your critical points and know that if there are any, they have to happen at those points. This, however, is not the same as going backwards. This does not mean that all critical points are extrema. I should note that this word extrema is just a fancy word for saying mins or maxes, minima or maxima. Okay, so not all critical points are mins or maxes, but all mins and maxes have to happen at critical points. So to help with kind of determining which critical points are going to be mins or maxes, we have a test. In Calc 1, we have two tests, the first derivative test or the second derivative test. Both give us valuable information, a lot of the same information. But we're going to focus on just the second derivative test as we're not going to have an analog for the first derivative test in functions of two variables. So let's review the second derivative test for functions of one variable. So if x equals c is a critical point, that means that f prime of c is equal to 0. Then we look at the second derivative. If the second derivative is positive, then we say that f has a local min at that critical point, x equals c. If the second derivative is negative, f has a local max. And if the second derivative is 0, we cannot say anything about it. We have no additional information. This test has not worked. This test is inconclusive. And that's going to be an important aspect. We're going to have a similar thing in our functions of two variables. So let's quickly review why this works, this second derivative test, as we should be able to kind of understand this. Let's look at the first one here. If the derivative is 0 and the second derivative is greater than 0, we know that this function has to be concave up. The second derivative is greater than 0. And since the first derivative has to be 0, we have a horizontal tangent line at that special point C. This is going to be the bottom of a valley, which means we have a local min. So although it may seem backwards that if the second derivative is positive, we have a local min, which we usually associate with something negative. If we think about the picture of a concave up function, we get a valley. We can think about the bottom of the valley. Similarly, for if it's concave down, we have the top of a mountain kind of kind of idea, and that would be a local max. Now, unfortunately, when we talk about functions of two variables, this visualization is going to be much more difficult to think about. But if we sort of go back to the second derivative test for functions of one variable, we are going to see the similarities, maybe can think about the visualization in that matter. All right, so now let's jump to new material. Let's talk about functions of two variables. Before we do that, before we look at the whole process, let's look at some examples and try to identify, just with a table, a contour diagram, and a graph, what are the global max and global min, and identify any local min and local max if we can see them. So first, let's look at the table here. We have a bunch of x values, a bunch of y values, and a bunch of function values in here. And with the table, it's kind of easy to identify what the global max and global min should be. It's going to be an estimate because we don't have all the values. But we're just going to be looking for the biggest function value and the smallest function value in our table. This is all the information that we are given. So the biggest function value happens at this 95, right? So we can say with some kind of confidence that the global max is going to be about at I should say global max is going to be at about x equals 0.2 and y equals 10. That's from these values right here. Now, that's not to say that there's not a bigger function value, near that 95, but since everything around it is smaller than that 95, we can say that the biggest function value should occur near there. Let's do the same thing for the min. The smallest function value on this table is this 65. That's not to say that that's going to be exactly the smallest value, but we can say with some kind of confidence, the global min is going to be at about 1.00, looking at the x and the y values. And again, everything around it is bigger than that, so we can say, again, there's something there. We also may be able to say that this value might be a local min. So again, what's the difference between a local min and a global min? They both have the idea that everything around them is bigger, right? They are the smallest function value near there, but it's not the smallest function value total. So for instance, also this 80 might be a local min because everything around it is bigger than it, but it's not the smallest function value. It's a valley, but not the biggest valley. All right, let's think about the contour diagram. So here we're given the function values as these lines, as these curves, these contours, and we can see that the biggest function value, the biggest contour that we see is the 8 on the right-hand side of that graph. So that means that that's going to kind of correspond to the biggest function value, and actually inside of that is going to represent values bigger than 8. Right? We are going up as we go inside that circle. So we can say that the global max will be right about there. We can say maybe that's at 6, 5. And the global max has a value of maybe 8.5 or something bigger than 8, but not quite 9, as we would have another contour there. Right, so the global max is the function value, and it happens at a certain point. The global min, we look at the smallest contour is the 3, and inside of that is going to correspond to a smaller function value. So this might be the global min, and it might be about maybe 2.5. And that's going to occur at the point 3, 2, looking at the x and the y values. And then we can play a similar game with local min, local max. It looks like this value right here is a local max. It's like the top of a little mountain there. Maybe it's about 6.5. And again, this happens at the value 2, 6. It's a local max, not a global max, because it's not the biggest function value. So we can get a lot of this information from the tables, from the contours, and that's kind of a big part of what we've talked about so far in this chapter, is how to use those two things to identify ideas of these functions. And finally, let's talk about this big graph here. We have this 3D looking graph. It has contours given by colors, right? So the red represents a larger contour, the blue represents a smaller contour, and we can see something about how we can see it has maybe 2 global maxes. That's okay to have more than one global max. Sorry, there's only one global max, but it occur at 2 different points. I'm not going to go over to what those points are. You could kind of find the corresponding X and Y values there, but that's not really the purpose of this course so much. And then we can see there are maybe 2 global mins, sorry, 1 global min occurring at 2 different points down there. There's not really any information to see if there's anything more than that in this picture. And again, that's why we use contour diagrams to identify or to look at these functions of 2 variables, because looking at the 3D graph can be cumbersome in some examples. All right, global max is the biggest, global min is the smallest, local max, local min are big and small, but not the biggest and smallest. All right, so now let's look at the process of finding the critical points and the local mins and maxes of functions of 2 variables. All right, so to find the critical points, we set the derivative equal to 0, but with functions of 2 variables, we have 2 ideas of the derivative, the partial with respect to x and the partial with respect to y. So to find critical points, we are going to set both partial derivatives equal to 0. Or we could find where they do not exist, but again, that's a little caveat that we're not going to think about too much in this course. That's true, but it's not going to be our big focus. So we're going to think about just setting those partial derivatives equal to 0. And then we're going to find points that satisfy both equations. And that's going to be an added difficulty, as it's not just one equation we're solving, it's 2 at the same time. And again, we're going to look at a bunch of examples to see how that will work. Then, similarly to functions of 1 variable, the goal is to use a test to classify those critical points as mins, maxes, or maybe neither, and maybe something else. And we're going to use a second derivative test. So here's the second derivative test with functions of 2 variables. Let CD be a critical point. So that is an xy point that the partial derivatives are both equal to 0. So again, f sub x is 0, f sub y is 0 at that point. And we are going to look at this new value, capital D. So this capital D looks kind of random, but let's just go through it real quick. You are going to look at all 4 different kinds of partial derivatives, f sub xx, f sub yy, f sub xy, and f sub yx. And I do want to just note where this comes from. So we're going to look at all 4, even though it looks like we only have 3 there. We have f of x, fxx, fyy, and then we subtract off fxy, and we actually have fyx here, but we know that fyx is actually the same thing as fxy, so we can write that as fxy squared. So if we think about maybe where this comes from, we have some kind of value that's letting us look at all 4 second order partial derivatives, even though it looks like we only have 3. And we have some kind of value that's going to tell us some information. To think about the math behind this, this comes from the Jacobian matrix and looking at derivatives, but that's a little bit beyond the scope of this course. All right, so this value D tells us some information. We know that if D is greater than 0, it's positive, then we know that the function is going to have either a local min or a local max at that point. And to determine if it's going to be a min or max, we do kind of the exact same thing we did for the first derivative test, and that is we look at the partial derivative with respect to x only, this fxx. In fact, you could do it with y as well, but let's just focus on the fxx. And you look, if it's concave up in the x direction, if it's greater than 0, we'll have a local min. If it's concave down, we're going to have a local max. And again, this would work for fyy as well. There's nothing special about fxx necessarily. This D is telling us something about how x and y are related to each other. And again, we won't necessarily go through the details there. Then we have if D is less than 0, we say that fxy is going to be or have a saddle point at CD. And we'll look at some visuals on the next page as to what it means to be a saddle point. And then, just like we had in the first derivative, the second derivative test for functions of one variable, if D is equal to 0, if this special value is equal to 0, we can't say anything about classifying those points. They could be mins, they could be maxes, they could be saddle points, they could be something else entirely. We have no information, and it is inappropriate to say anything. You can't even say, I think it might be this, because it gives you no information there. All right, so this is very similar to our second derivative test before, but obviously is more complicated as we have some more things to calculate. All right, let's look at this idea of saddle point before we do a quick example. So a saddle point, especially if we look at the thing on the right here, is a point where it is a min in one direction and a max in the other direction. Why is it called a saddle point? Because it looks like a saddle that you might put on a horse. But again, what does this actually mean? It is a min or max in both the x and the y direction, but it is the opposite. So if we think about here, in one direction, we have that this point represents a maximum. And in another direction, this point represents a minimum. So if you look in the x direction, it might be a maximum. If you look in the y direction, it might be a minimum. So if you look at it all together, it's something special, that's for sure. And we call that a saddle point. It's not a min or a max, but it's something kind of both at the same time. If you think about it in a contour diagram, right, you have, if you look at one direction here, just kind of following that and what contours it hits, it goes from 900 to 700 to something below 700, back to 700, back to 900. That's a valley. And if you look at the other direction, it goes from 300 to 500 up to some special point, back to 500, back to 300. That's the top of a mountain. And again, that's the same idea, that it's a max in one direction and a min in the other direction. All right, so we have three different kinds of points. We have a maximum, a minimum, and then the special thing, a saddle point. So let's look at a quick example before we look at the next video where we go over more practice. Let's find all critical points of the function x times y. And we're going to classify each point as a local max, local min, a saddle point, or of course it could be none of these, as something crazier might happen, or maybe we just don't have enough information to identify these. So our first step is always going to be finding the derivative. In this case, the derivative means two different things. We need to find the partial with respect to x and the partial with respect to y. So f sub x here is going to be the derivative of xy with respect to x. We think about y as a constant. If you think about y as a constant times x, the derivative will just be that constant y. And if you think about it, f sub y will be very similar. You'll just have x. So to find the critical points, we're going to set both of these equal to 0. And we're going to solve both equations at the same time. This is not a very difficult thing to solve as it's already solved. We get that x has to be 0 and y has to be 0. So we get a critical point of 0, 0. And that's the only critical point that we have. We'll look at more difficult problems in the next video. All right, so that's half the battle. Find the critical points. The next battle is classify these points as local maxes, local mins, or saddle, or classify this point as a local max, local min, or saddle point. So that is, we're going to look at the value D, which is fxx fyy minus fxy squared. So we need to find all three of those second order partials. So fxx is the derivative of y with respect to x, and that's going to be just 0. fxy, which is the same as fyx, is the derivative of y with respect to y, and that is 1. And fyy is the derivative of x with respect to y, that is a 0. So this value D is going to be 0 times 0 minus 1 squared. So that is a minus 1. Since that is less than 0, we have that 0, 0 is a saddle point of this function. It is the special value that it's a min in one direction, a max in the other direction. So that's from the second derivative test there. Now let's look at a visualization of that function so we can kind of see what it means by saddle point again. So here's a picture of x, y in a contour diagram and a three-dimensional drawing where the contours are actually drawn on the diagram. And we can see that the special point 0, 0, so here's y equals 0, here's x equals 0, corresponds to right in the middle there. We can see that this is kind of a min in that direction. It looks like the kind of bottom of a valley. And it is a maximum in the other direction, as it looks kind of like the top of a parabola, top of a mountain there in that direction. Even though we're kind of going like diagonals there, it doesn't have to be exactly x direction, y direction. We can kind of see that sort of saddle shape there. And if you think about the contour diagrams here, if you go in one direction here, it goes from small to big to small. It's top of a mountain. And in the other direction, same kind of thing, big to small to big. Now, again, this may be a little bit weird because we're going in sort of a diagonal direction, but again, that's not really the importance here. The importance is kind of what is a saddle point. And that means that if you look in one direction, it's a min. In the other direction, it's max. It doesn't have to be necessarily the direction of x and y specifically. So, here's the direction of just y. Here's the direction of just x. And we don't get that saddle point-like idea. In fact, it's kind of like constant on that part. But if we look at, a special direction, we can sort of see that. All right, in the next video, we'll do some more examples, look at more complicated functions, and try to identify these critical points.